Good morning. This is group number 1 with the topic Entangled Strain Quantum Cryptography Eavesdropping on the Ekert Protocol. This is Vishnu Kumar, roll number 23N0299. Let me go through the abstract of this paper. This paper basically explores about the quantum cryptography because as we know that as we are progressing toward the quantum computer, then the classical cryptography will be no longer useful because the classical cryptography relies on the hardness of problems, mathematical problems like factorization of large prime numbers, which will be done by quantum computer in a relatively very small time. So it will not be safe and secure very soon. So we will have to go towards the quantum cryptography, and the same is the theme of this paper, that it's talking about how the quantum cryptography can be obtained by the pair of entangled photons. Entangled photon pairs obtained by the parametric down conversion process. Uh, so this paper basically talks about the quantum cryptography and also the Benz inequality violation. The two of by two measurement we have in this paper, it is shown that the quantum cryptography is very much eavesdropping proof, or we can find out whether the Eve is listening to our conversation or it is eavesdropping or not. Okay, so basically this is the basic theme of the paper, and it is saying that by no means uh, the complete secure cryptographic key can be violated by the Eve without knowing by the Alice and Bob that their key has been compromised. Okay, so let's talk about the experimental setup of this particular paper, that how they have done this. Yes. So here you can see that this is the experimental setup where we are giving photons. We are giving photons from this AR plus laser, uh, and then there are two BBO crystals with their optical axis perpendicular to each other. And it is such that, or it is oriented such that the incident photons from the AR laser is incidenting at an angle of 45 degree, making with either of the uh, optics axis of the BBO crystal. Uh, One is at 0, one is at 90. So the our incident photon is making its angle at the 45-degree incidence. What does this it implies? It implies that due to the high spatial overlation between the two BBO crystal, which is very small as 0.6 micrometer, and also the coherence produced due to the laser, uh, there is equal probability of this incoming photon to parametric down converse in both either of the crystal, that it can parametric down convert either in the first crystal where its optic axis is, let's say, at 0 degree, or in the second crystal where its optic axis is 90 degree, because the incident has the same angle and they are coherent, and also high spatial overlap is there. So what does it helps in achieving? It helps us achieving in maximally entangled state given by phi plus h1 h2 v1 v2 by root 2. Also, as soon as sorry for this mark, yes. So as soon as these two photons or a pair of photons is created, one is sent to the allies from this path, one is sent to the Bob from this path. Okay, and the allies has a setup where it has liquid crystal. Liquid crystals helps it in attaining the polarization basis or the measurement basis in with the help of these angles phi 1, phi 2, phi 3, phi 4. Because as we change the liquid crystal or its orientation, then what will we get? We will get different phase angles, which will introduce different phases, like it is shown here, that their measurement axis will depend on h1 plus e to the power iota alpha v1. So this alpha here is decided by this liquid crystal, and we can change it with the help of our liquid crystal. And after that liquid crystal, we have half wave plate. Half wave plate is used so that it can introduce the diagonal basis, because the wave plate here is oriented at 22.5 degree. What does this 22.5 degree helps in achieving is that, as we all know, that the half wave plate uh, bends, or it rotates the phase or polarization of phase of any incoming wave by the 2 theta, like if the incoming if its x is at 22.5 degree, then the 2 theta will be 45 degree. So incoming incident beam will be rotated by an angle of 45 degree, and hence it can be helped for the Bell inequality violation. Okay, measuring the Bell's inequality. Then we have this beam splitter, prism beam splitter, which will separate the incoming beam in either of the one orthogonal uh, basis, measurement basis, and then it will send the beam either in the detector 1 or at the 1 bar. Similarly for the bob, in either of the detector 2 or 2 bar. So this is basically the experimental setup where a photon from AR laser will be incidented on two BBO crystal with their optical axis perpendicular to each other. The incoming photon will strike at an angle 45 degree with either of the two axes. Then the two photon generated in pair will be sent to the allies and both each, uh, and then with the help of liquid crystal they will choose their measurement basis, uh, alpha 1 alpha 2 or beta 1 beta 2. Then the half wave plate will be there to introduce an diagonal basis by rotating the uh, outcoming, or the we can say the beam coming from the liquid crystal by 2 theta, that is by 45 degree, and then that beam will strike on the prism beam splitter, which will again uh, break this and will send at either of the one detector, either one or at one bar, uh, depending on its uh, depending on its measurement or its basis. Okay, and here it is also shown that E will be here at either of the one channel. We have taken the Bob, that Alice is secured network, but in the channel of Bob, Eve is doing its measurement. So this is basically our experimental setup where Eve will do two different types of measurement. And yes, this is pretty much our experimental setup. Here we have used the silicon avalanche photodiodes for detection. uh, our polarizing beam splitter is there, liquid wave crystal plate, and yes, the argon ion laser is of 351.1 nanometer, uh, and BBO crystal beta barium borate. Let's move to the mathematical setup part. Okay, so we will go through the mathematical setup. First of all, we can see that because of the high overlap and the coherence between the two BBO crystal and the photon pairs that will be generated will be maximally entangled state, that is given by pi plus H1 H2 V1 V2 by root 2, where H and V represent the horizontal and vertical polarization respectively. To analyze these entangled state, Alice and Bob will measure the photons in their related basis, that is given by H1 plus e to the power iota alpha V1, and similarly for base where alpha and beta can be manipulated with the help of the liquid crystals. Here in this paper they have used the four different bases: alpha 1, alpha 2, alpha 3, alpha 4, as given here, and similarly for the Bob, the beta 1, beta 2, beta 3, beta 4. Now, our initial state of the photons is given by this psi plus, and the analyzing basis for Alice and Bob's are given by this e to the power iota alpha and e to the power iota b, as you can see psi a psi b. After normalizing them, we will get these two basically analysis basis. Now, because these are the one basis, we also need their orthogonal basis, which will be detected at the detector bar. Like this will be detected at 1, this will be detected at 2. So their orthogonal states, that is given by this. This is 1 bar and 2 bar. These are obtained with the help of the orthonormality conditions of the eigenstates. Now, the probability of finding P12, that means that the detector 1 and 2 click simultaneously. As we know that the final state for detector 1 and 2 are given by phi A and phi B. So we will use the final state and the initial state and their inner products modulus square as the standard probability definition in the quantum mechanics. Uh, on doing this particular calculation, we get that uh, we get this particular expression for the inner product as described in these three steps that I've done. And taking the mode of this particular square will give us this, as we will only take the real part for the probability thing. thing, and you can do this at the simple a plus b whole square and e to the power 2 into e to the power iota alpha plus beta, and uh, this is basically, and we have to take the real part of this divided by 2, so we will get 1 by 4. Okay, now let's so we will get the probability for at detection at 1 and 2 simultaneously, given by 1 plus cos alpha plus beta by 4. Similarly, for detection at 1 and 2 bar, simultaneously we will get the probability as 1 minus cos alpha plus beta. Now, similar to P12, we will also get P1 bar, 2 bar, that the simultaneously detection at the 1 bar and 2 bar detector. And same goes with 1 bar, 2. So this is P12, this is P1, 2 bar. These four are same. Now let's go ahead for the result. Okay, yeah. So basically we get these result at our detector side, and we connect them with the AND gate in the end. Now, after performing their measurement, the Alice and Bob will disclose their respectively bases, and we will only use those bases where alpha plus beta is equal to 180 degree. Alpha plus beta is equals to 180 degree, because in that particular case, what we will get for P12 is 0. Because cos 180 degree is -1, and 1 minus 1 will give us 0, while as 1 2 bar was basically 1 by 2. I apologize. Here it is given wrong. This is not 1 bar 2 bar. It is 1 2 bar. Okay. Uh, we will rectify it, and then just like here we have done it. Alpha 1, beta 1, alpha 2, we will make this table, and here we'll only use those bases where this condition is satisfied. Now, as you can see that from here, our alpha 4 is 180 degree, and beta 1 is 0 degree. So alpha 4 plus beta 1 corresponds to quantum key. So in similar fashion, we have calculated all this, and we can say easily that the only those bases whose alpha plus beta correspond to 180 we will take, while we will take rest of other for the our Bell's inequality test given by S and S bar, because two tests are being performed. Now also their detector signals are properly synchronized, and they are filtered using AND gates, allowing only signals that arrive in a very short time window, that is of 5 nanosecond. This greatly reduces accidental detection that is sometimes created by double photon pair creation. Each of them controls their liquid crystals using separate computers, which are precisely synchronized through waveform generator card, where a valid detection event occurs. A digitalizer records the LC states and the signals from all four detector pairs, ensuring accurate measurement and data collections. Okay. My name is Vishnu Kumar, and this was up here. This was my part, and my roll number is 2300299. And now I'm passing off to my other team member.
Moni. Hello everyone, myself Muskan, and my roll number is 2300330. Now I'll be explaining to you about the probability and bit error calculations and their significance in this paper. So, what we are proposing is, let's say we have a coincidence rate of 5000 per second, and we want to measure in a time window of 1 millisecond. So, if in 1 second we have 5000 counts, that is photon pairs, then in 1 millisecond we have 5 photon pairs generated. So this is the average number, which we call lambda, of the photon pairs in our experiment. Then we now want to calculate the probability of detecting at least one photon pair in 1 millisecond. This can be calculated from the formula which we follow for Poisson distribution, which is given by probability is equals to e to the power minus lambda to the power n upon n factorial. So we want to calculate for the probability of observing at least one, which should be given by this. It should be 1 minus P0. So plugging in the value for n equal to 0 and lambda equals to 5, we get this approximately to be 99%. So there are very high chances that in this time window we will get some photon pair. Also, there is one more fact that we want to if we want to calculate the probability of having more than one photons, then it will be given by 1 minus p0 minus p of 1. And after putting in the formula, we will get these values to be around 96%. So from here we can say that hmm, there is very high chance of observing more than one photon pair in this time window. So this is an issue, and we want to prevent this because during each collection window, the phase settings remain constant. And if there are multiple photon pairs produced, then eavesdropper can potentially use them and analyze them for getting the information about the random alpha and beta basis generated in the collection window. So to prevent this issue, what we will do in a single time window, we will just measure a single measurement and discard the other bits. So this rule is called one pair per window. So after this, we want to analyze the data collection rate and how this relates to the usable rate. So the LC which the authors have used in the experiment have a cycle period of 22 milliseconds. That is 22 milliseconds contains one cycle. Then 1 second will contain 1 over 22 millisecond, which will be equal to around 45 bits per second. So in 1 second, so this is the rate at which we are getting the information of the key bits. But what happens is that the usable rate is a bit lower than this because sometimes the LC voltages are in transition when the digitizer attempts to read them. And during this transition, there is ambiguity in the measurement of the phase because we are not certain what is the phase. So they are basically the false measurements. So we want to avoid them, and by discarding them, we will get the usable rate around to be 40 useful photons per second. So instead of 45, we have reached to 40, which is around 80% efficiency of this process. Next, we want to address one more issue, which is the double pair generation. Sometimes there is double pair generation by the BBO crystal, and that occurs to that has measured to be occurred around 0.7% of the times. This data is experimental, and this happens due to the 5 nanosecond gate window because in that time we can have more than one photon pairs. But this introduces a minor risk in the security, which we will have to include in our error calculations. Also, one more point about this will be for the better performance of LCs, the 22 millisecond cycle period can be reduced to 19 millisecond for better calculations because if this reduces, then our information per second will increase. So if we heat the LCs to 35 degrees Celsius and increase the voltages, then we can get improvements, that is a 19 millisecond cycle period. So after this, if we finally want to get into the error calculation part, then if you look at this diagram, this states that the used data for the cryptographic key is only 25%, as we have already seen in the table. And we will use 50% of the data for testing the Bell's inequalities, and the rest 25% is discarded due to ambiguities in the error. Due to ambiguities in uh, the error introduced by the angles. Okay. Then we will talk about the raw bit rate now. So in the measurements, we have taken 10-minute runs 4 times. So there are a total 40-minute runs which are run, and we have collected the bits which were found to be 24252, so which is around 24,000. So around 24,000 bits we have calculated in this 40 minutes. So the average bit rate will be simply this 24,000 divided by 40 into 60, which will come to be 10 bits per second. So in these calculations, the experimental bit rate error was found to be around 3%, which we rounded off to 3.4 for which is conservatively taken to be 3.4. So, and we are assuming that this whole information goes to Eve, and Eve uses it to intrude and get the information. So the total error will be that 0.7% from the double pairs and 4 by root 2 times of this 3.4%. I will explain how this 4 by root 2 factor comes. So this adds up to 10.3%, which makes 10.3% of these 24,000 bits to be around 2500 bits. So this much information Eve can use to get our data. So how this 4 by root 2 factor comes, let's talk about that. Suppose the Eve intercepts the x bits, and we know that it introduces an error of 25% when Eve intercepts. So the error bits will be 1 by 4th of this x, and this x will be 40. So this is the minimum number of bits subjected to this intercept resend strategy. But there comes only the factor of 4 if we want to explain this 1 by root 2 factor. Then what Eve does is, Moni. Hello everyone, myself Muskan and my roll number is 2300330. Now I'll be explaining to you about the probability and bit error calculations and their significance in this paper. So uh, what we are proposing is, let's say we have a coincidence rate of 5,000 per second, and we want to measure in a time window of 1 millisecond. So if in 1 second we have 5,000 counts, that is photon pairs, then in 1 millisecond we have 5 photon pairs generated. So this is the average number which we call lambda of the photon pairs in an experiment. Then we now want to calculate the probability of detecting at least one photon pair in 1 millisecond. This can be calculated from the formula which we follow for Poisson distribution, which is given by probability is equals to e to the power minus lambda to the power n upon n factorial. So we want to calculate for the probability of observing at least one, which should be given by this. It should be 1 minus p0. So plugging in the value for n equal to 0 and lambda equals to 5, we get this approximately to be 99%. So there are very high chances that in this time window we will get some photon pair. Also, there is one more fact that if we want to calculate the probability of having more than one photons, then it will be given by 1 minus p0 minus p of 1. And after putting in the formula, we will get these values to be around 96%. So from here we can say that there is very high chance of observing more than one photon pair in this time window. So this is an issue, and we want to prevent this because during each collection window, the phase settings remain constant. And if there are multiple photon pairs produced, then eavesdropper can potentially use them and analyze them for getting the information about the random alpha and beta basis generated. Issue, what we will do in a single time window, we will just measure a single measurement and discard the other bits. So this rule is called one pair per window. So after this, we want to analyze the data collection rate and how this relates to the usable rate. So the LC which the authors have used in the experiment have a cycle period of 22 milliseconds. That is 22 milliseconds contains one cycle. Then 1 second will contain 1 over 22 millisecond, which will be equal to around 45 bits per second. So in 1 second, so this is the rate at which we are getting the information of the key bits. But what happens is that the usable rate is a bit lower than this because sometimes the LC voltages are in transition when the digitizer attempts to read them. And during this transition, there is ambiguity in the measurement of the phase because we are not certain what is the phase. So they are basically the false measurements. So we want to avoid them. And by discarding them, we will get the usable rate around to be 40 useful photons per second. So instead of 45, we have reached to 40, which is around 80% efficiency of this process. Next, we want to address one more issue, which is the double pair generation. Sometimes there is double pair generation by the BBO crystal, and that has measured to be occurred around 0.7% of the times. This data is experimental, and this happens due to the 5 nanosecond gate window because in that time we can have more than one photon pairs. But This introduces a minor risk in the security, which we will have to include in our error calculations. Also, one more point about this will be for the better performance of LCs, the 22 millisecond cycle period can be reduced to 19 millisecond for better calculations, because if this reduces, then our information per second will increase. So if we heat the LCs to 35 degrees Celsius and increase the voltages, then we can get improvements, that is a 19 millisecond cycle period. So after this, if we finally want to get into the error calculation part, then if you look at this diagram, this states that the used data for the cryptography key is only 25%, as we have already seen in the table. And we will use 50% of the data for testing the Bell's inequalities, and the rest 25% is discarded due to ambiguities in the error. Due to ambiguities in uh, the error introduced by the angles. Okay. Then we will talk about the raw bit rate now. So in the measurements, we have taken 10-minute runs 4 times. So there are a total 40-minute runs which are run, and we have collected the bits which were found to be 24252, so which is around 24,000. So around 24,000 bits we have calculated in this 40 minutes. So the average bit rate will be simply this 24,000 divided by 40 into 60, which will come to be 10 bits per second. So in these calculations, the experimental bit rate error rate was found to be around 3%, which we rounded off to 3.4, for which is conservatively taken to be 3.4. So, and we are assuming that this whole information goes to Eve, and Eve uses it to include and get the information. So the total error will be that 0.7% from the double pairs and 4 by root 2 times of this 3.4%. I will explain how this 4 by root 2 factor comes. So this adds up to 10.3%, which makes 10.3% of these 24,000 bits to be around 2,500 bits. So this much information you can use to get our data. So how this 4 by root 2 factor comes, let's talk about that. Suppose the Eve intercepts the x bits, and we know that it introduces an error of 25% when Eve intercepts. So the error bits will be 1 by 4th of this x, and this x will be 40. So this is the minimum number of bits subjected to this intercept resend strategy. But there comes only the factor of 4 if we want to explain this 1 by root 2 factor. Then what Eve does is she aims to maximize her knowledge and minimize the error. So she uses the Breed-Bart basis, which are given here, this and this. So these are basically 45-degree rotated bases between the rectilinear and the circular ones, so that the Eve maximizes its probability of guessing the correct results. So if you want to calculate P correct, which is we can calculate this by say the Alice sends this 0-degree state, which we can call as H as well. So if sends 0-degree state and Eve measures it correctly in this basis B1, then the probability of this correct results will be cos square pi by 8. Similarly, in second basis, it will be sin square pi by 8. But since we want to maximize this, then this comes around to be 85.4, which is around 2 plus root 2 upon 4. But we are taking value rather than we are taking this 1 by root 2 value, because we have implied privacy amplification processes. So this comes down to 1 by root 2. So here is our final expression, which is 0.7 plus 4 by root 2 times 3.4, which comes to be 10.3%. So now we want to calculate the residual information which Eve has now. Okay. So also I would like to mention that for the net bit rate after the privacy amplifications is this much, because we have removed the bits out of those 24,000 bits. We have removed the ones which had some ambiguities. So the net bit rate is now left to be 6.4 bits per second only. Now I would like to calculate the residual information which we will have after all these privacy amplifications. So here we'll be using two theorems directly taken from this paper. So these relates the important quantities, like let n be the length of the originally transmitted bit string, and k be the safety parameter that we will use for error detection, that the bits after the filtered bits which we'll have. Then the first theorem states that if phi is in permutation from here to here, and these two functions defined over these permutations, then f and gx defined to be these, then the knowledge of phi yields no information on g except their lengths are same, that is n minus k. Then the second theorem simply states that the mutual information which E will get after all these privacy implications is 2 to the power minus s upon ln 2, where s we can say is any non-negative integer smaller than n minus k, and in this case it is the security bits. So if you state all these values, n is given around, so this is n, which is the filter bits after error correction, then k after privacy implication, and 2500 these bits we had to remove because these were directly available to Eve. So using theorem 2, we will get this factor around 2 to the power minus 234, which is very less. In fact, it is 10 to the power minus 107. So this is the information which Eve will have after privacy amplifications, which is way less than 1 bit. So this guarantees the confidentiality of the transmitted key, making it suitable for the cryptographic use. Thanks.
Hello, my name is Pratibha, and I'm going to explain Bell parameters, and also about Bell inequalities. So I'm going to start with Poincare sphere. Poincare sphere is basically a 3D geometrical representation of polarization states of light. So as we can see, on the horizontal plane, we have the vertical. On the equatorial plane, we have the horizontal and vertical polarized light. And on the north pole and south pole of this sphere, we have right circular and left circular. And in this particular paper, they have, instead of using linear polarization analysis, they have used elliptical polarization analysis. And they have calculated two main Bell parameters, that is S and S prime. And this S and S prime are given by this two equation, where E is the correlation function, and the correlation function is defined by this, where R is the various coincidence counts between Alice and Bob detectors. So according to classical physics, this Bell parameter S and S prime has an upper bound, and that upper bound is 2. And Bell's inequality also tells us about the probabilistic relation between how a photon fails a test and how a photon passes a test. So if we assume like we have a polarizer, we have a in Bell's tests. Let's say there are 3 tests, A, B, and C. The A test is that the analyzer axis is vertical, and for the B test, the polarizer is at an angle theta, polarizer B, and for the C test, the polarizer is at an angle 2 theta. So basically what Bell's inequality tells us that the probability of A B bar plus the probability of B C bar will be greater than probability of A C bar. So we know the probability that a photon passes through an analyzer, it will be cos square theta. Like if we assume like this is the electric field vector and this is making an angle theta, this is our polarizer axis, and the probability that the light passes through this polarizer will be cos square theta, and probability that the photon does not pass through it will be sin square theta. So from this we can calculate P of A B bar, probability that the photon passes through A and photon fails to pass through B. That will be, and we also know that the cos square theta average sin square theta average will be 1/2. So from this we can calculate P of A B bar as half sin square theta, and also P of B C bar also as half sin square theta. So this will be greater than P of A B bar. P of B C bar will be greater than P of A C bar. A C bar will be half sin square 2 theta because it's making an angle 2 theta here. So basically this S parameter is proportional to half sin square 2 theta. And here in this particular experiment, first they have proven that the Bell's parameter S was found to be greater than 2. So this is a clear violation of Bell's inequality. They got a value like 2.6 around. So this clearly shows a violation of Bell's inequality. So now let's take a look at the derivation of Bell's inequality. Suppose we have a detector we have two detectors, A and B, and we can calculate the correlation function, and which is defined as the expectation value of measurement outcomes A and B. A and B are basically the measurement outcomes, and small a, small b are the detector settings, and lambda is a set of hidden variables that determines the outcomes. So we can define the Bell parameter S like this, and by substituting S E in this equation, we will arrive at this form. And we know A and B, the measurement outcomes can take plus or minus 1. And if we assume that B is equal to plus 1, B at a particular detector for a particular lambda, and for small b setting, it is plus 1, then B prime lambda, if we take it as minus 1, the first term in this integral will become plus 2, and this will vanish. So even if we take it the other way, one of the terms in this integral vanishes. So this integral always comes out to be plus or minus 2. And we also know that P of lambda is normalized. So we can say the Bell's parameter will be, mode of Bell's parameter will be less than or equal to 2. This is a classical case. Using quantum mechanics, we can also derive that S is equal to 2 root 2. It is greater than 2 in case of quantum mechanics. And the proof of that is also given here. Like we have defined the correlation function again as expectation value of the product of measurement outcomes. And since here we have assumed a source and then two detectors, which is measuring at theta 1 and theta 2 angles, two detectors, and we know the probability will be the product will be either plus 1 or minus 1. So two possibilities for plus 1 and two possibilities for minus 1. And then we have taken using this equation for probability and we know the state psi, which is our entangled state, h1, h2, v1, v2 by root 2. And also we know a1, e2, and substituting all of this into this probability equation, we will arrive at this half cos square theta 1 minus theta 2. And we basically have to find s, so we'll substitute this in E. And finally, we will arrive at this E equation, cos 2 theta 1 minus theta 2. And for maximum violation, and we know the maximum violation occurs at this particular angle, theta 1, 0, 3 pi by 8, minus pi by 4, and pi by 8. And substituting this equation in S equation, we'll arrive at 2 root 2. So this is the proof for quantum mechanical Bell's parameter upper bound. So if there is a presence of eavesdropping, this Bell's parameter, we expect, or in this paper also they have found the Bell's parameter have decreased, and the bound, it was found to be less than or equal to root 2. S Eve is found to be less than or equal to root 2. And also this Bell's parameter in the case of quantum mechanics was found to be greater than 2, and it was a deviation from Bell's inequality by 34 sigma. And we can also check the eavesdropping potential, if there is a potential eavesdropper or not, by using minimum bit error rate also, by checking if it is more than 25%. So that's it.
Hello, I'm Bonnie Roy. My roll number is 23N0320. So now we are going to talk about methods that Eve can eavesdrop on Alice and Bob's communication. So the two methods are beat error rate, or BER, and another one, non-demolition, or QND. So for the first one, communication, there she accidentally introduces an error. So that will be half will be the probability that Eve will be choosing wrong basis, and because of choosing her choosing the wrong basis, that will be another half. So the probability of total error will be 25%. Or see, we have plotted 3 bases. First one we can see here. The first one is for S, and the second one is for BER. For S, we can see classical Bell's inequality threshold is 2, and quantum mechanically that will be 2.2 root 2 or 2.8. So as we can see, a theoretical value we have got for this case, that is below 1.5. So that is definitely a quantum mechanical case. And also when we have plotted this experimental values for both strong basis and QND, they actually satisfies, they are quite close to the theoretical value we have calculated. And for the BER, we can see 5%, and also the experimental value that we have found from an app by calibrating the graphs we found on the paper. So close to the value 25%. Now, then when we are using this second basis, what we can see, this one. This. Is our second graph. We can see that this two graphs actually the theoretical value pretty much matches the experimental value that we have found. So again, the diamond one is for strong basis, and the circular one is for QND. And again, for this one is for the S, and for BR, we can see this has also matched very goodly to the experimental value. The 40 plus 45 and minus 45 degree. For this third basis, graphs for S and BER. The graph quite did not match well, but for the second one, it is very, we can see it has fitted very well with the value. And again, this diamond one is for the polarizer, and the circular for QND atoms. So now I'm going to introduce quantum and non-demolition, or QND, eavesdropping. So what happens, as we have seen in BER, when we are measuring, it is expected that we can introduce some error to the photon or the measurement. So, but the theory for the quantum non-demolition is that we want to measure the entangled photon, which actually does not affect the cryptogenic security, or the photon state does not get changed due to the measurement. So first, we can see the entangled photon state is given by this. And we have used this, the can be given as half of sine theta 1 plus theta 2 whole mod square, which was proved by Pratibha, who was present. So now, and also she has also proven this Bell inequality. So now we can see the interaction Hamiltonian for this is given by NSNP, where H cut is the, as we, the nonlinear coupling constant, and NS and NP are the photon number operator for single mode and probe mode. So now I would like to actually discuss the. So as we can see here, we will first send the source through a calcite crystal, and then we will have two orthogonal beams, and then we will introduce QND to one of them. And here we can see the zoomed version of the QND. So here the signal, when the signal comes through the mirror one, it will go along this path through the care medium, and through this mirror too, it will get out. And while going through this mirror, we will find another beam which will reflect through this M2. So through beam splitter will reflect and transmit the probe 50-50. So get reflected through mirror one, and here the signal and the probe will interact, and thus we will have this Hamiltonian H1. So as we can see here, H cut is the reduced Planck's constant, chi is the nonlinear coupling constant, Ns and Np are the photon number operator for single and probe mode.
And then we will have this quadrature amplitude, where B dagger is the creation operator and V is the annihilation operator. And N is as well, we can say the number operator signal. And then we will have the signal to noise ratio, where C0 and C1 are the um, and C0 is the peak for 0 photon, and C1 is the peak for 1 photon. And this is the average separation of this two peaks of 0 and 1 photon. And del C0 and 1 square, this individually represents the variances of each. And then when we will introduce chi equals to pi, then we will have the SNR max, which will be 2 to the power 2/3 into alpha, where alpha is the coherent probe amplitude. State of QND interaction. After post interaction, we will have this state. This is our final state. And after this QND interaction, we will have diagonal terms. And now we will see that this is the damping factor. So, and when we will have pi equals to phi equals to pi, then we can see that we will have gamma equals to ex into mod of alpha square. And finally, after introducing this damping factor to the probability, this joint detection probability as this term, half into sine square theta1 plus theta2, and this is the extra term that we are having due to the interaction. We will finally have this Bell inequality valuation parameter S, and then we can see this. There is this also this factor gamma damping factor. Have a damping factor, or like but when we will try to reduce this gamma, in order to reduce gamma, we will actually this parameter S, and where for earlier it was explained that we need to basically maximize S so that we can have it more than the threshold value quantum mechanically, that will be around more than 2 root 2 or 2.8 and something. So we will see that it will actually it will be impossible to implement QND practically, because when we will try to reduce gamma, we will actually reduce S, and so this Bell inequality threshold will not be satisfied. This practical limitations, where we can see this real care non-linearity. Phi equals to pi, our would be around 10 to the power 6 km losses, noise, and phase drifts. And that's all. Thanks.
So we are into the final part of this presentation about the summary. And we have what we have gone through this paper. Okay, just give me a second. Okay, this paper sharing secret information using the quantum physics, which is important, which is impossible using a conventional or even a quantum computer. The author specifically implies the Ekert protocol, which has been explained by the other team members, a quantum key distribution method that uses the entangled entangled photon pair to share a secret key between the two people, like Alice or a Bob, and detect the Eve and try to spy them. Okay, so let's have a small look what's the Ekert protocol is all about. So, unlike the protocols that use weak laser pulse, this protocols use the entangled photon, which in a quantum way. So if one is measured, the other result instant effect, no matter what the distance is. This connection can't be faked or copied without being detected. It simply means that if Eve is there in between, Bob Bob will going to Bob and as will going to get an immediate information that someone is there. The Ekart protocol checked the spy by testing Bell's inequality and a quantum rule that must be violated if the photon are truly entangled. If Eve interferes, this violation decrease and alert Alice and Bob. Okay, let's have a look to the experimental setups that been is been already explained by the Vishnu in the starting, which is this particularly this part. So let's have a there so for how we generate the photon, entangled photon was created using the spontaneous parametric down conversion in special crystal. So Alice and Bob, which got one photon and randomly measures its polarization using a different settings. Key creation. So when these setting match, when these key Bell's inequality. This helps to check if there is any Eve. They only keep the first detection event in which the time window to avoid the coupling multiple players, which could leak extra information to Eve. So in the same paper, the author tests two possible strategies Eve might be used to like certain information. The first one is encrypted and resend. Means Eve will going to take the photon. Eve measures a photon and send a replace to the Bob. This introduces an error in the measurement. All right. The second one is quantum demolition attack. The theoretical model means this is theoretical model photon. Is a theoretical model is not yet been possible, and this is simulated using the spatial crystal, means some hypothetical crystal. All right, so these both strategies were found. Eve present could be detected because the error rate is increased or the Bell's inequality violation is decreased. This experiment also shows if Eve guesses the wrong measurement basis, the error rate will increase from 25% to 250%, making it easy to detect. So now let's have a look how the security test we have done in this experiment. We measured 24,000 raw bits in a few 10 minutes. After all the calculation and privacy amplification, they we got that 15 bits. Uh, and the observation bit error rate was low, about 3%. The Bell's perimeter, which is S, was around 2.6, which clearly is much more than a classical limit, which is 2, means entangled and Eve isn't interfering. Now, the future potential of this experiment, we have created a table for the experiment. This setup can be scaled to hundreds of meters or even to the satellite, enabling the global quantum communication. In conclusion, this was the first experiment to use entangled photon in a full quantum cryptography protocol. It successfully demonstrates the Eve can't be detected, laying the ground for the real world secure quantum communication over a long distance. All right, thank you.